Diffraction. Diffraction refers to the spreading or the bending of plane waves when they encounter an aperture. Okay, if you look at this animation here, this shows an aperture. So the plane waves, when it pass through the aperture, they start to curve. So this is the bending or the spreading of the waves. They also start to spread or bend when they encounter an obstacle. So as you can see here, this add light and obstacles. The linear dimension of the obstacle or the aperture have to be comparable to the wavelength of the waves. The wavelength of the wave is given by the distance between the wavefront. So the distance between the two wavefronts should be approximately the same as the width of the aperture. Similarly, the size of the obstacle here, it should be comparable to the width of the obstacle. Okay, when we say comparable, we are referring to the same order, need not be the same value. Next, we are going to watch a video on aperture and diffraction. Okay, in lecture, I stopped at 1:18, but since this is a recorded lecture, we actually have all the time for this. We'll watch the full video.
The next thing I want to look at is what happens to a water wave when it passes through an aperture. Well, I've fitted an aperture here, but it's rather too wide for what I need at the moment. So if I fit these sliding doors, I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of the wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to know that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction. Well, I'm now going to return the aperture to its original width and take a look at the effect of changing the wavelength of the wave. Now remember, I can change the wavelength by altering the frequency of the paddle using this controller here. If I make the wavelength longer, you can see that the waves become more spread out beyond the aperture, more diffraction. If I make the wavelength smaller again, that's where we started, an even shorter wavelength, then there's less diffraction. So here are the two separate factors that affect the diffraction of a wave passing through an aperture. The wave spreads out more if the aperture is made narrower, or if the wavelength of the wave is increased. And conversely, it spreads out less with a wider aperture or a shorter wavelength. In fact, all kinds of waves, not just water waves, exhibit diffraction at an aperture, as long as the aperture is not too big.
Okay, so with that, right, we can see that there will be significant spreading only when the width of the aperture or the obstacle is comparable to the wavelength of the waves. And one thing I want you to take note is, in general, diffraction increases with longer wavelength, because when the wavelength is larger, then there will be more spreading. The reason to this is actually from the wave theory, Huygens principle. We will look at that in the next lecture under single slit diffraction. Another important feature is that the wavelength remains the same before and after diffraction. Okay, so if you look at the distance between the two wavefronts here, okay, it should be the same as the distance between the two wavefronts here after it passed through the aperture. So lambda should stay constant. Okay, so with that I finished section 3.